So we left off last time talking about three-phase, and I wanted to talk about three-phase power. We'll look at three-phase power in terms of a Y. This is definitely a Y system. And we'll also look at a delta. And by the very fact that we're looking at both of them, should give us a hint that their conclusion is probably going to be the same, because if one provided more power with less input, that would probably become the standard, and the other one would become a footnote in history. So it shouldn't surprise us that the final equation that we get for both of these will be the same. Well, I've laid out this circuit with a Y. I haven't annotated the whole thing, but over here, if I take the A phase, this would of course be the B phase and the C phase, and I've shown the phase voltage. Remember, the phase voltage by definition is the voltage at the line with respect to the neutral. This would be the A impedance and then the B impedance, and this is talking about the load. We could make this same argument for the source if we're talking about power supplied, but it's probably a little cleaner and easier to think about if I talk about the load and power absorbed. So if I think about this voltage, this phase voltage AN, and then this line current I little a big A, I could say that the power that we're dissipating here, in A is equal to the magnitude of that phase voltage times the magnitude of the line current times the cosine of the angle between those. That's our old friend we saw a long time ago. Average power was equal to VRMS times IRMS times the cosine of the angle between those two quantities, right? So hopefully that's fairly straightforward. And we could say then, if we wanted to, that the power in A phase should be equal to the power in B phase should be equal to the power in the C phase, because they're all balanced. They should all be the same, right? And then we could say that this is the power per phase. So the power per phase would be equal to, why don't I call it V phi, that's the magnitude of the phase voltage, and I phi, the magnitude of the phase current, times the cosine of theta phi. And I'll have to be careful about that theta phi. I'll come back and talk about that some more. So if I wanted to talk then about total power, I could say that total power, P sub T, for all three phases would simply be 3 times the power per phase, right? Which would be equal to 3 times V phi times I phi times the cosine of theta phi. Well, with the Y, the line current and the phase current is really the same, isn't it? This current's the same in the Y. So whether I say I line or I phi, that's really the same. The phase voltage and the line voltage are very different. And a lot of times I want to talk about this in terms of a line voltage. So why don't I talk about this in terms of a line voltage? I'll say that this is going to be 3 times. If I want to talk about this in terms of a line voltage rather than a phase voltage, could I say that I have the line voltage here divided by the square root of 3? Is that fair? Yeah, that would work. And I could say then that I phi is really just the same as I line. So if I talk about it in terms of line quantities, which is probably a little more common, I could say that. And then we have the cosine of theta phi. So if I tidy this up, remember that 3 is going to be just 2 times the square root of 3. Or I'm sorry, it would be square root of 3 times square root of 3, or the quantity squared. So I could cancel that and just leave a square root of 3 in the numerator. So I could say then that the total power is equal to the square root of 3 times the magnitude of the line voltage times the magnitude of the line current, which in the Y is the same as the phase current, times the cosine of theta phi. Okay. And that's our final result. That's the total power. We'll use that equation. We probably won't use it as much as you think we probably won't use it as much as we think we might, because we can still go back and just use V squared over R or I squared times R, and I'll show you those in an example. The one thing that you have to be very careful of this is that this angle here, while we're talking about the line voltage and the line current, that angle is still the angle between these two entities. So it's the angle between the phase voltage and the phase current. Okay, it's the angle between the phase voltage and the phase current. It is not, I repeat, it is not the angle between the line voltage and the line current. So that's an important point to remember. Okay, a lot of times we don't have to sort it out because we know that angle is also the power factor, isn't it? Okay, so if we have the power factor, we don't even have to mess around with that. Well, we could take this into the complex realm. We could say that Q, remember that complex power, S, is equal to power plus JQ, right? We're looking at complex power. So if we talk about Q, the reactive power, we've seen that before, that would be equal to V phi times I phi times now the sine of theta phi. Or we could say that the total Q, this would be the Q per phase, that the total Q would be equal to 3 times the reactive power per phase, which would be equal to the square root of 3 times the magnitude of the line voltage times the magnitude of the line current times now the sine of theta phi, which again we have to observe is the angle between the phase voltage and the phase current. So this one also works for reactive. You just change your cosine to a sine. Really just the other leg of the triangle when you think about the power triangle, right? And we could, if we wanted to, also talk about S. I mean, it still holds that the complex power is going to be V phi times I phi conjugate. That would be for one phase, and you could multiply it by 3 and get the total if you want to. So all of our power equations still work, but we added this one to it, and you have to be a little bit careful with that. So that's for the Y. Are there any questions with that? Well, let me go on and do the very similar work for the delta. So I don't have my backing sheet here, so it doesn't turn out too bad. Okay, so here is more power. With the delta. Okay, and that's not to say this gives you more power. This is just continuing. Maybe I should say continuing. Okay, continuing the power discussion with the delta, because we'll find that these are both of the same efficiency. So I draw this delta. I purposely drew it a little different than you've seen, probably seen it before, but if you look at it and analyze it, you look at these 3 points right here, and right there. That is indeed a delta, although it looks a little bit different. And again, I've really only annotated the AB phase here. So I've got voltage A with respect to B, and then I've got this current here that is the current from A to B. So I've got the phase current, and I've got the line voltage. And I could say then that the power here, the power that's dissipated there, is going to be equal to VAB times IAB, the magnitudes of those, times cosine of the angle between them. Again, our power calculation. So we could then work our way through this and say that the power in the A phase would be equal to the power in the B phase would be equal to power in the C phase. It didn't come out so well. Power in the C phase, which is going to be power per phase that we could say was equal to the phase voltage. Because remember, the phase voltage in the delta is line to line, isn't it? Times the phase current, that's the thing that's changing in the delta, times the cosine of theta phi. And we could then further say that the total power is going to be equal to 3 times the power per phase, because there's 3 phases. So I have 3 times V phi times I phi times cosine of theta phi. And again, I'd like to use line quantities. So I'm going to write this as 3 times, remember that the voltage, the phase voltage and the line voltage is the same in the delta, so I can just say that this is V line, they're one and the same, but the current is different. The phase current is related how to the line current? You're all experts on this because of the lab, right? As far as I'm talking about the magnitude's pretty easy. The angle sometimes you have to think about, but the magnitude is pretty easy. The phase is always less, so I'm going to have to take the line current and divide by the square root of 3 to get that phase current, right? So that's a substitution for that. And then I have the cosine of theta phi. Well, again, I recognize 3 as being root 3 times root 3, and I cancel one of those, and I can say then that the total power is equal to the square root of 3 times the magnitude of the line voltage times the magnitude of the line current times the cosine of theta phi. And again, we put a box around that. We recognize that is exactly the same one that we had for the y. Okay, so there's no power savings. It's not like you can go home and, if I change my delta to a y, I'm going to save a few cents each month. Not true at all. Okay, that's why we have both these systems still around, because they're both equally efficient. The one thing that we have to be careful of here is, again, that this is the angle between what? Phase voltage, which is the same, and the phase current, which is different than the line current. So that's a big one that you need to remember. Yes? Well, you can remember that while they might be both equally efficient, one may dissipate way more power in terms of, remember that the z for the y is equal to z for the delta divided by 3. So I might go down and maybe buy a heater, a 3-phase heater with resistive elements in it and has a fan blowing across it. And the elements, they might give me instructions on hooking them up into a delta, and maybe it's going to dissipate 30 kilowatts. And if I hook them up into a Y, maybe it's only going to dissipate 10 kilowatts. So there is a difference there. But given the power put in, the power put out is just as efficient. Yes?
In your first equation there, you said the cosine is theta y sub a the same as
yeah, we should, didn't I did that with phi there, didn't I? So I should probably be consistent and say phi there, yes. It's the phase angle of the current. We usually use the symbol phi, so thank you. Other questions? So yeah, if you have something and you hook it up as a delta, it may perform differently as a Y, but given your power input, each one, power inputs of terms of voltage and current, each one is going to be just as efficient. Okay. Okay. Well, with those, I'd like to look at an example that we've been doing. You should have a handout on this one. This is our 3-phase problem here. So we're going to look at and ask questions about the power on this one. We probably won't do the delta, because our delta looked very much like a Y when we looked at the model there. I think we can get lots of good practice with this one. So you may want to pull out that handout. I reproduced a lot of our work from that. So if you go back a day or two in lecture, you'll see that we took that example and we turned it into a single-phase equivalent circuit where we had the source here. We had the line here, and we had the load over here. And if it makes people more comfortable, you can connect those two neutral points up. You saw in laboratory in vivid fashion that there really isn't much current there. If there's not much current, you don't need a conductor, do you? If it was perfectly balanced, like our circuit here is on the page, you don't need a conductor there. And I think last time we talked about the current I, little a, big A. That should be in your notes. We talked about the phase voltage across the load. That should be in your notes. Remember, these are all in RMS values unless told otherwise when we're in 3-phase. And then we talked about the line voltage, not the phase voltage, but the line voltage across the load. We had something like that. You remember those values? So I'm not going to reinvent the wheel there. I'm going to take those as on face value and start to talk about the power in this thing. So let's talk about the power dissipated in the load. Maybe I should talk about real or average. And maybe I want to talk about total. So the total real or average power dissipated in the load. What's that look like? Well, that's our equation from before, isn't it? We could say that the power total is equal to the square root of 3 times V line times I line times the cosine of theta phi. So if I were to go through that, what's that going to look like? Do I have a, well, root 3, that's easy enough. And what's my line voltage? The magnitude of that is 199.58. Is that right? Where's my line current? Line current and phase current's the same here, 2.4. I've got that. Times the cosine of the angle of the voltage. Now, while I used this voltage here, is that the angle that I want? No, I want the angle up here, minus 1.19, subtract the angle of the current, which is going to be a minus 36.87. And let's see what that turns out to be. So 673.9. It's got too many significant figures, so you know where it comes from. 673.9, and this is watts, right? Real power, average power, it's watts. Okay.
So the negative 1.19, that came from DAN, but in our problem, in the magnitude, we
right. That was the exclamation point thing here. So while I'm using the magnitude of the line voltage and the line current, the angle is the difference between the phase voltage and the phase current. I'll put another exclamation point. Thank you for asking that.
I don't know why the phase current will be equal to
the Y, the phase current would be equal to, yes, the currents are the same. Yes. Okay, are there other ways of doing this? I mean, I like power problems because there's lots of ways to do them. I mean, this seemed like the logical way here. We just study an equation, we're good students, and we do it like the equation we just saw. But are there other ways to do it? Yeah, I mean, we could break this up many different ways. We could say that the power per phase is equal to, how did that thing start out? We had, what, V phase, I phase times the cosine of theta phi, which would be, what do we have, 115.22 times 2.4 times the cosine of, again, the cosine would be exactly the same thing there, minus 1.19 minus a minus 36.87. What's that turn out to be? I think if you run the numbers, someone can check that out. You should get 224.6 watts. Anyone got that? Okay, on, that's good. Now it looks like that differs, but remember this is for per phase, so if I multiply this by 3, what do I come up with? Yeah, I should come up with that 673.9, right? Anyone confirm that? Good. Okay, I got a thumbs up. Great. So that's another way of doing it. The important thing is to recognize that you know what you're doing. Are you finding total or are you finding per phase? You can get there either way. Now, I'm never a big fan of learning equations that will suffice for things I've learned in the past. I mean, we have a situation here. We're really looking at just this load. I mean, we could look at the entire system. If we had more time, we'd spend talking about, well, what's lost in the line, and adding the line and the load to get what's supplied and so forth. But our lesson can be learned just as well if we look at what's going on with the load. What do I have? I've got a resistor. I've got an inductor. Right? There's N. There is A. This is what? 39 ohms. And this is J, 28 ohms. Is that right? And I have a current going down through here. I'm told that this current is I little a big A, isn't it? So could I not say that the power that's being dissipated here is equal to I RMS squared times R? Is that fair enough? I don't put the half in there because I'm using RMS values, so I'll say 2.4. Whoops, that's not power dissipated there. Power dissipated there, isn't it? We'll get to the other one soon enough. There we go. So the power dissipated in the resistor, I squared times R, is going to be 2.4 squared times what's the resistor? 39. When we run the numbers on that, what's that turn out to be? 224.6 watts. And we recognize that up there. That works for phase. Multiply that by 3 and you'd have that done, right? So there's nothing mysterious about three-phase power. The biggest thing is to try and keep careful accounting. Are we talking about total power? Are we talking about power per phase? What's the situation? Now, could we use power is equal to V squared divided by R? Yeah, you could, but what voltage would you want to use? Yeah, you'd have to use this voltage here, wouldn't you? Which do we know right now? We actually don't know right now. We know the voltage across both of those. That would be VAN, but you would not want to use VAN for that. Everyone understand that? Okay, so while this is an okay equation, we tend not to use it that much because current goes through both things. Voltage is not across. We don't want the voltage across both things. Well, the last thing we should probably do here is maybe talk about the reactive power. So what is the, maybe I'll do that down here, reactive power dissipated in the load? So how could you get that? Well, I mean, you could do this a variety of different ways. We could say that total reactive power, Q sub T, would be equal to what? The square root of 3 times VL times IL times now the sine of theta phi. We saw that equation, so we can use it. Square root of 3 times 199.58 times 2.4 times the cosine of what we have, minus 1.19 minus a minus 36.87. Yeah, it should be sine. Absolutely should be sine. Thank you. So let's see what that turns out to be. Uh, 483.9, is that right? What's the unit on that? Bars, yeah. Bars. Okay. So that would be fine. I mean, sometimes they'll talk about magnetizing bars. What's the magnetizing bars displaced and whatnot. We shouldn't be intimidated by that. We don't do that calculation probably as much as we do average power. But could we get this with one of the different ways? I mean, you could, if you wanted to, say that per phase it's equal to V phase times I phase times the sine of theta phi, which would be, what did we have here? 115.22 times 2.4 times the sine of, again, minus 1.19 minus a minus 36.87. You could go through that. That's kind of boring to do that. Maybe I could do it a different way. I mean, when you got that, you multiply it by 3, and it better come out to be that. Let's do it quicker than that. What would be another way to get it per phase? How about our old friend I squared RMS? Take the RMS value, which everything's in RMS here in 3-phase, and we're going to put our X sub L in there. The imaginary portion of the impedance, right? So what would this be? 2.4 squared times, we've got now 28. So this should be 161.3 bars. Now if I multiply that by 3, what do I get? 483.8 bars. I got a little round off in there, but I think we're okay. Anyone run this number here? 161.29? Yeah, so I think we're good. So lots of ways to do these. Unfortunately, there's lots of wrong ways, but there are lots of right ways. Now, with as far as we're talking about the load, if I want to talk about S, let's say for the load, what could I do? Well, I could just say that that was P for the load plus JQ for the load, right? So what are we going to have? If I do this for the total load, I'm going to take 673.9 plus J, 483.9, and that would be volt amps, right? Now let's see, could we do this another way? Yeah, we could say that S per phase would be equal to the phase voltage in phasor form times the phase current in phasor form, and I have to do the complex conjugate, right? Didn't I have that one? Did I put the conjugate on that one? Yep, there we go. Right there, good. Okay, so let's see if we can do this. What was our phase voltage? 115.22 at an angle of minus 1.19. And I'm going to multiply that by the phase current, which is the same as the phase, or which is the same as the line current in this Y. So 2.4 at an angle of minus 36.87, right? Instead of taking the conjugate, I'll just go ahead and put this as positive and indicate that's the conjugate, right? That's not a mistake this time, but it was a negative. I made it a positive, so that means I took the conjugate already. So we hammer through that. What do we get? I get 276.5 at an angle of 35.7. 0.68, which is, I mean, that's okay for an answer, volt amps. Probably what I'd like to do is put that in a rectangular form so I could reconcile it hopefully with this, right? So I'll switch to a rectangular form. There we go. 224.6 plus J 161.3 volt amps. Have I seen some of those numbers before? Yeah, right. Remember the 224, so if I multiply this by 3, let's see what we get. 673.9 plus J 483.9 volt amps. Did we do good? Yeah. Okay.
What do we call the S again? Is it complex power?
S is complex power. Mm-hmm.
And Q is
Reactive power. And if you look at a power triangle, remember that P is down here and the real power, average power, Q, reactive power is there, and then S is on the hypotenuse. Okay. So, I mean, it was worth remembering these equations that we developed for the three-phase, but oftentimes you don't need them. So don't make this more complicated than it needs to be. Let's finish up with one last problem in power. This is a homework problem, so you have the problem. You can go look it up. It's homework number 32, so it's getting close to the end of the homework problems that could possibly be on the exam. And we're told that a balanced three-phase source powers two loads. The first load is 36 kilovolt amps at 0.8 power factor, and the second one is 18 kilovolt amps at 0.6 power factor, both of them lagging, so they're both inductive, right? The other thing we want to start thinking about is they have given us what in these? If this is 1, they have given us kilovolt amps. They've given us the hypotenuse, haven't they? So this is 36K. And could I come up with the angle in here? Yeah, I know that the arc cosine of the power factor should give me that angle. Let's see. So that is what? 36.87? Yeah. Now one thing that I think I want to do before I get too carried away on this is this is total for each load. So we would take that as all three of the phases. Okay. Now that's something you always want to try and get resolved. Are they talking about a single phase? Are they talking about the all three of the phases? Well, we're going to take this as all three of the phases. So I think what I'm going to do is I'll analyze this for one phase. So that 36K would go to what? 12K, right? Okay. So 36K is going to go to 12K. Then I have this theta in here, 36.87. So that means that I could find these other two sides. I could say that this was 12K times the cosine of 36.87, which would just be the power factor. And then I have over here 12K times the sine of 36.87. When you do that, this is 7,200 bars. And this turns out to be 9,600 watts. So that's what I know about the first load. So let me do something similar for the second load. Again, I'll take the arc cosine of the power factor, which is 0.6. This is going to give me a bigger angle, 53.13 degrees. So I can draw that triangle. degrees, 53.13 degrees. And I know the hypotenuse there is 18 kilovolts, but I'm going to divide it by 3, right? Kilovolt amps. So that turns out to be equal to what, 6? So here I have 6K times the cosine of 53.13, and here I have 6K times the sine of 53.13. This turns out to be equal to 4,800 vars, and this turns out to be 3,600 watts. Okay. So far so good? So if I wanted to talk about, let's say, S2, I could say that it was 3,600 plus J 4,800, right? And if I wanted to talk about S1, I could likewise say that that was 9,600 plus J 7,200. And if I added them up, what would I come up with? $13,200, is that right? Yeah, 13,200 plus J 12,000. Yeah. Okay, and that would be volt amps. Because what I would like to do is by putting these together, I can say the combination of these is this power triangle that looks like this. That I have 13,200 watts here. That I have 12,000 vars here. Because one of the things that I'm looking for is the combined power factor. And I can get that pretty quick with that arrangement that I have there. Because if I look at this thing here, the cosine of that angle is the power factor, isn't it? So let me talk about that. Let me say that theta is then equal to the arctangent of the opposite side, 12,000, divided by the adjacent side, 13,200, which gives me 42.27, 42.3 degrees. So I could say then that the total power factor for the whole system would be equal to the cosine of 42.27, which gives me 0.74. That would be... I think just the cosine. The power factor is equal to the cosine of the phase shift. So that turns out to be 0.74 lagging. So now we know what those two are, which makes sense. It's between those two. It's fairly easy to think about since they're both lagging. Then the other thing that I wanted on this is I wanted to find the line current. So maybe I want to think about a model of this thing. I would have some voltage source here. I'm going to draw just one phase of it. So here I will put load number 1. And here I put load number 2. And I'll have something like this. So this would be the A, and this would be the neutral. So I've drawn the single phase equivalent circuit. And we're told then that if I combine this, I really have a system now that looks like this, don't I? I combine those loads into one single load. Okay. That was 13,200 plus J 12,000 volt amps. This is the total. And then this voltage source. What do we have here in the given? We're told that the magnitude of our line voltage is 208. So if I'm drawing the single phase equivalent circuit, this is the phase voltage. So what's this going to be? 208 divided by the square root of 3, which should net me what? 120? 120.1. Let's take it as 120. So now we can go back, and if I want to try and find this current here, I can use our power equation. Remember the old equation we had? Power was equal to V RMS times I RMS times the power factor, the apparent power times the power factor. So I'm going to solve for the magnitude I RMS. I can say I RMS is equal to the power divided by VRMS times the power factor. So what power did we have? That's real power, 13,200, divided by VRMS, 120, and the power factor. What's the power factor for this whole thing? 0.74, isn't it? So this gives me an answer of 148.55. That's the magnitude. Let's see. I need an angle, don't I? I mean, if I'm to answer this and get done with this on a Friday afternoon, I need to come up with the angle. So I have 148.5, or 6 if you'd rather, at an angle of, do we know what our angle is? Yeah, the angle for the entire load is right there, isn't it? Okay. And if we took this voltage reference, if I take this as a reference of 0 degrees, what's this angle have to be? Negative 42.27 degrees, right? Because we're told that the voltage and the current is going to lag by that angle. So that's how we pick up that negative sign there. So just because we're studying three-phase doesn't mean that you want to forget everything else that you learned about single-phase analysis and everything that you learned about single-phase power. So we used a lot of that in this problem. It was definitely a three-phase problem. A lot of times where you can get in trouble in the problem is, are they talking about ohms per phase or total resistance? Are they talking about power per phase or the total power? So those are things to look for as you go through the problems. Well, that gets us to our stopping point on three-phase. When we get together next time, we'll start talking about mutual inductance and transformers.